now see why we should use strict dominance here in the definition of dominance frontier, or actually not strictly dominates. If we look at this graph, and we can say that there is an increment of a variable I in vertex 7, then clearly we need a phi function for I. And in this case, 7 is both U, predecessor, and V. And therefore it's added to its own dominance frontier. Okay, so that's the reason. And now we will see how to compute the dominance frontiers. So from the definition, recall the definition. And we have the children here. It means a child in the dominator tree. And the dominance frontier is computed bottom up in the dominator tree. And we use two separate computations and take the union of them. The first is df local, which is very simple. It's we look at a vertex. Well, we can actually see the definition. It's the easiest. So for each successor v of u, if u does not strictly dominate v, then v should be in the dominance frontier of u. I mean, we put it in df local, and the dominance frontier is the union of df local and something else, which we will look at soon. For instance, for 7, we add 5 to df local, and also we add 7 itself. Okay, df up takes a subset of the dominance frontier of a node and give that to the immediate dominator of that node, or to the parent in the dominator tree. I mean, that's the same. So df up is used by the parent in when the parent computes its dominance frontier. So what we do is to check every vertex in the dominance frontier, and if edom of C, which stands for child, does not strictly dominate that vertex, then it is added to df up. And df up of C is given to the immediate dominator of C. We can note that we don't have to check for dominance. It's sufficient to check for equality. Yeah. Okay, so well, that's what we already said. So we can leave that, and and we look at df up instead. Okay, so as I mentioned, this is the contribution from a child in the dominator tree to its immediate dominator. We can start with an example. 7 is a child of 6 in the dominator tree, as can be seen here. And 5 is in the dominance frontier of 7. 6 needs 5 in its dominance frontier. And okay, so what we do is to check each vertex in the dominance frontier of 7, and those nodes in the dominance frontier which are not strictly dominated by 6 are put in df up 7. Okay, there are 2 nodes in the dominance frontier of 7, namely 5, and 7. And 6 strictly dominates 7, so it's not added to df up 7, but 5 is. Okay, so why does this make any sense? The question is, why is df up of a child a subset of the dominance frontier of the immediate dominator of this child? Okay, so let's look at any vertex in the dominance frontier of C. There must be a predecessor of V which C dominates. Okay, and then the question is, does the immediate dominator of C also dominate this predecessor? I mean, does the immediate dominator of C dominate P? It must, because dominance is transitive, and clearly the immediate dominator of C dominates C. So the immediate dominator of C must also dominate P. Okay, so then it's sufficient to check if if the immediate dominator strictly dominates this vertex V in the dominance frontier of C. And that's exactly what df up achieves. Okay, as I mentioned, we can simplify this slightly by using equality check instead of dominance check. This is shown in the book, but we will not go into that. I also mentioned that that we can check dominance. For instance, well, say we want to know if U dominates V, then we can follow V up in the dominator tree and see if we reach U. It's an exercise in the course to simplify this, so that we don't have to traverse the dominator tree, but we can do something quicker. Okay, I just inform you that it's possible, but I won't tell you how to do it. There is a hint in the exercise. So, how do we compute the dominance frontiers in a control flow graph? Well, we start with the dominator tree, and then do a post-order traversal. That means we compute it bottom up. So we start with saying that the dominance frontier is of a vertex is the empty set, and then we compute df local of that vertex, and then what we see here is that there is no representation of df up. It's used in the theory, but we don't store it explicitly. We compute it on the fly, so to speak. So when we are computing the dominance frontier of U, we check the dominance frontier of each child and then each vertex in the dominance frontier of that child, and see if we dominate that vertex strictly or not. And depending on the outcome, I mean, if U does not dominate this vertex strictly, or actually if U is not the immediate dominator of this vertex, then we add it to the dominance frontier of U. So this is the first that you will implement in lab 2. Okay. Well, this is what I already remarked.